Hi and welcome back to today's video. Today we're going to talk about two important characteristics of vector fields that you frequently encounter in practice. And those characteristics are called rotation and divergence of a vector field. We will not use those characteristics a lot and will not discuss them in depth, but I still find it important to introduce them because they appear in many practical applications in engineering. So you should have an idea of what you're talking about if you encounter rotation or divergence anywhere. Okay. One remark up front. We will only define rotation for vector fields in R3. Formally, you could also introduce a similar characteristics for higher order vector fields, but we're not going to do that. And in practice, you will mostly see them used in dimension 3 as well. There's rarely something like rotation used in higher dimensions, although it's theoretically possible to do something similar there. But we're going to concentrate on dimension 3 for the rotation. The divergence is a general concept that can easily be generalized to higher dimensions, so we'll just do that as well. Okay, quick remark at the beginning. So we will introduce two important characteristics of vector fields that are frequently encountered in applications. And those are called rotation and divergence. I'll give you the formal definition first. We'll start with the rotation, and then I'll give you an idea of what those mean, how those can be interpreted. And of course, we'll also see a couple of examples. So let's start with the definition of rotation. We will need a vector field, of course, so let V be a vector field, and we'll define that on R3. You could also take a domain that's part of R3. That vector field needs to be differentiable. And then we can define the rotation. Sometimes also called the rotor of V is the vector field denoted by rot V, rotation of V, defined as, and the definition is the following: the rotation of V is defined as a vector field that consists of compositions of partial derivatives of components of V. Sounds more complicated than it actually is. I'll just give you the formula, and then I'll give you a means to remember that, hopefully. Okay, so the formula is that's dV3 dx2 minus dv2 dx3. Then in the middle we have dv1 dx3 minus dv3 dx1. And finally, dv2 dx1 minus dv1 dx2. Okay, so that is a vector field, a characteristics that is a vector field again. To help you remember that, there is a memory aid that's used very often, also in formal notation sometimes. What the rotation of V really is can be abbreviated in a way by taking the nabla operator that takes partial derivatives with respect to the variables x1, x2, x3, and then taking the cross product of the nabla operator and the vector field. So basically what you do is you apply those partial derivatives to the components of the vector field, v1, v2, v3, as if you would compute a cross product. And you all know that only works in R3, right? So be careful about that. But the rotation is, as we define it, is only defined in R3 anyway. Okay, so that's a way to memorize that formula easily if you know how the cross product works, of course. And also you will notice that the expressions in here, those should look familiar if you know about integrability conditions for vector fields. Those are exactly the conditions that you need to check for integrability conditions of a vector field in R3. So in R3, the integrability conditions can be expressed by just saying the rotation of the field is the zero vector. So again, a little remark. The integrability conditions for vector fields in R3 can then simply be expressed as the rotation of V is the zero vector. And that's again something that you'll often encounter in practice. Now what does rotation do? I'm not going to explain that in lots of details. Basically the idea is to measure the local rotation as experienced by a particle that is moving along the vector field. And that amount of rotation is then distributed or is then applied to the resulting vector field in a perpendicular way, so to speak. We'll see that what that means in the examples in just a minute. Okay, let me just get you that idea. So the rotation of a vector field is very roughly a measure for local rotation of a vector field as experienced by a particle moving along the field. So you have a particle that's propelled forward by the forces in the vector field, and from the point of view of that particle, if you look around standing on that particle, then you will experience a rotation of the flow around you generated by that vector field, and this is more or less what this rotation actually expresses. Okay, let's give you a few examples. Example number 1. Let's take V of x1, x2, x3 to be the vector field that consists of just x2 and then all zeros. So that means if we were to draw just the plane part of that, right? So just want to see what happens for a fixed x3 coordinate. So we have x2 here, x2 here, x1 there, and we wanted to draw that field. Then what happens here is the flow changes with the x2 coordinate. So for any fixed x3 coordinate, the vector field looks like this. If x2 is 0, then nothing happens. Right, so that's all 0 vectors. If x2 increases, then we get a flow in x1 direction, like this. And if x2 increases even more, then that flow increases. And if x2 goes below 0, then we again get a flow in x1 direction, but it's reversed. So we get a flow like this here. And as x2 increases, that flow gets a little larger as well. Right? So imagine you're sitting on one of these flows here. You're moving along with a particle. Would you experience a rotation if you look around? And although it looks like this is not a rotation at all in the vector field, you would still experience rotation here. Because if you're moving along the field, looking up, then particles above you would move faster. Particles below you would also move faster, but in a different direction. So there's some rotation around you as you're moving. And that's what is actually expressed in the computation here. So if you compute the rotation of the vector field, by just applying the definition, let's have a look at that. So basically V2 and V3 are 0. That means nothing is happening here. That's just V1, and that is x2. So that is also 0. That's 0 anyway. The only non-zero part will be this one. So we get dv1 by dx2, that's a 1, and we have a minus in front here. So what happens here is we just get a -1 in the last component and zeros everywhere else. Okay, so that indicates there is indeed some amount of rotation in that vector field from a particle's point of view that's moving along that field. Example 2, one more example here where you can actually see the rotation of the vector field. You do remember that we introduced rotating fields in dimension 2 already. And of course, we can just extend those by more or less ignoring the third component. So we can just ignore x3 and set the resulting x3 to 0. And what we get is then again a field that is the same for every possible x3 coordinate. So basically the result here looks like this. So we have x1, we have x2. And imagine x3, those are just stacked on top of each other. And what happens here is, at the origin, there's nothing going on again. As you move away from the origin, you will experience a motion like this. And as you move farther away from the origin, that increases. So what you get here is indeed a rotation in that field. Yeah, you can see that hopefully. And that means, of course, the computation of the rotation should express that as well. So let's see how that works. I'll show you the memory aid for once. So we can also use that. So let's see, that's gradient times v. So that means we have ddx1, ddx2, ddx3. Cross product minus x2, x1, 0. And then let's compute the result. This cross product is basically computed in the following way. So for the first row, you ignore the first row. And you just take the second and the third row like this. And then what you do is you compute the determinant of that, and that's the result of the first row. So in this case, determinant of that here, that means ddx2 of 0, that's of course 0. ddx3 of x1, that's again 0. So we just get 0 minus 0. For the second component, you do pretty much the same. You ignore the second row, so you just take row 1 and row 3. And you compute the determinant created by the matrix here, those 2 by 2 matrix. This time you need to add a minus sign. So as with determinants, the sign changes. First row is a plus, second row is a minus, third row will be a plus again, right? So that's minus this determinant now. And that means you compute ddx1 of 0, that is 0. ddx3 of minus x2, that's again 0. And with a minus sign, you get minus 0 plus 0. And finally, let's ignore row number 3 and determine this determinant here. ddx1 of x1, that is 1. So finally, something interesting happens. Minus, and here you get ddx2 of minus x2. So that's a minus 1. And that means we get minus minus 1. So the end result is 0, 0, and plus 2. So that is the rotation of this vector field here. Yeah, and again, remember, this is just a convenient formalism. We did not really specify operations like this, but it's probably a good idea to remember it in that way if you know what the cross product does, and you probably know. Okay, so that's how you compute the rotation of a vector field. Now, let's move on to that other characteristics that is called the divergence. Again, I'll start with the definition. So the divergence, the definition of that is a whole lot simpler than that of the rotation. Again, we need a differentiable vector field, so let's start with that. Let V Rn to Rn be a differentiable vector field. Then the so-called divergence of V is the function div of V of x, defined as the sum over I equals 1 to n of the partial derivatives d vi dxi. So you just take the first component, you differentiate it with respect to x1, the second you differentiate it with respect to x2, and you sum up all of these, and then you get a function that maps a point in your domain in R to the n to a real number. So that is actually a function that maps div v that maps R to the n to R. So the rotation was a vector field. The divergence is a scalar field. And again, there's a simple memory aid here, although that is probably a little too simple to justify a memory aid. But you could say the divergence of a vector field, that is basically the scalar product of the gradient and the vector field. So you apply that operator ddx1 to v1, you apply ddx2 to v2, and so on up to ddxn, which you apply to vn. Okay, so that can be used to remember what the divergence of a vector field means. What it does as an interpretation, basically the divergence measures the local density of sources and sinks. So basically it measures how much outflow in the first component in direction of that first component, how much outflow of the second component in direction of the second component, and so on. Yeah, so if there's local sources or local sinks of the vector field, that should be reflected in the divergence. So you could say the divergence is a measure of local density of sources and sinks of a vector field in a certain way. Yeah, don't take this too literally, please. Again, a couple examples. So divergence can be applied to vector fields in any dimension. So we'll start with a simple two-dimensional vector field here, v of x1, x2. Let's just say it's something like x1 and x2 squared. And then the divergence of that is, well, we need to differentiate the first component here with respect to x1, so that derivative is 1. And we need to differentiate that second component with respect to x2, so that's 2x2. So this is the divergence of that field. And one more example, one in dimension 3 here. V of x1, x2, x3 is defined as minus x2, x1, and x3. And the divergence of that field, now remember, that is basically d dx1, d dx2, d dx3 applied to the field, so minus x2, x1, x3 of x. So differentiating this with respect to x1, that yields a 0. Differentiating this with respect to x2, again yields a 0. And finally differentiating this with respect to x3, that yields a 1. So the divergence here is simply 1, independent of the x. Okay, so that's something that is pretty easily computed, but again, it appears frequently in applications, especially in engineering applications. Okay, so now you know these two important characteristics of vector fields, rotation and divergence, and that concludes this video here. I'll thank you for your attention, and I'll see you in the next videos.